On the morning of May the 10th, 2024, a farmer in Iowa stood in his field watching his $500,000 GPS-guided tractor lurch sideways. The machine carved crooked lines through freshly tilled soil, its autopilot system completely blind. He grabbed his phone. 23 messages from neighboring farms. Same problem, same chaos. Miles away in Kansas, another farmer's precision planter had stopped working entirely, frozen mid-row. In Minnesota, autopilot systems were failing across thousands of acres of prime farmland. Within hours, the disruption spread across the American heartland. Not from a computer virus, not from a cyber attack, but from something 93 million miles away, something most people never think about until it's too late. The sun had just unleashed one of the most powerful geomagnetic storms in 2 decades. GPS satellites, floating 12,000 miles above Earth, suddenly couldn't tell farmers where they were. Position data was off by up to 230 feet. For precision agriculture, where every inch determines whether crops grow in optimal conditions or wither in compacted soil, it was catastrophic. By the end of that weekend, American farmers had lost between $500 and $565 million. Entire planting schedules collapsed. Crops went unseeded during the critical window, and most people, checking their phones for photos of the northern lights, had absolutely no idea. That storm has a name now. Scientists call it the Gannon Storm, after the space physicist who helped document it. And here's the part that should terrify and thrill you in equal measure. It wasn't a freak accident, it was a warning. Hello there, and welcome. I'm so glad you found your way here tonight. If you've been watching the skies lately, if you've seen reports of auroras appearing in places they shouldn't, if you've wondered why the northern lights keep reaching farther and farther south, then you're already part of a story that's unfolding right above us. Because something extraordinary is happening, and almost nobody saw it coming. On October 15th, 2024, NASA and NOAA made an announcement that changed everything we thought we knew about the current solar cycle. The Sun, they confirmed, has officially entered solar maximum, the peak of its 11-year cycle of magnetic fury. But this isn't just any solar maximum. The Sun fooled us. Every expert, every model, every carefully crafted prediction. When Solar Cycle 25 began in 2019, scientists looked at the data from the previous cycle. Solar Cycle 24, which had been the weakest in a century, and they made their forecasts. They predicted Solar Cycle 25 would be similarly weak, peaking around mid-2025 with a smoothed sunspot number of about 115. Research papers were published. Budgets were allocated. Space agencies planned their missions around a quiet, manageable sun. Then reality laughed at their predictions. By August 2024, the smoothed sunspot number had reached 156.7, shattering forecasts by more than 35%. On October 3rd, 2024, the sun produced an X9.0 solar flare, one of the most powerful eruptions ever recorded, bright enough to be detected by instruments on Earth even through the blazing light of day. And in May, that G5 geomagnetic storm, the first in over 20 years, didn't just create auroras visible in unexpected places. It cost more than many hurricanes. This solar maximum isn't following the script. It's stronger, faster, and more chaotic than any cycle in recent memory. Scientists who've spent decades studying the sun are scrambling to understand why their models failed so completely. And we're living through it right now, you and I, at this very moment. So tonight, as you rest, as your breathing slows and the day's tensions fade away, we're going to drift through this cosmic moment together. We'll explore what the northern lights truly are, not just as beautiful phenomena, but as visible evidence of forces that could, if unleashed at full strength, bring our technological civilization to its knees. We'll uncover why this particular solar maximum surprised everyone. We'll journey from the surface of the sun to the upper reaches of Earth's atmosphere, and we'll discover why, despite the risks, this is also one of the greatest opportunities any of us will have in our lifetimes to witness one of nature's most spectacular displays. You don't need to do anything but rest. Let your thoughts settle. Let the wonder wash over you like those auroral waves we'll soon be exploring. Because the lights in the sky are calling, and the sun has a story to tell. If these calm, curious explorations bring you peace or spark a gentle wonder as you drift toward sleep, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now let's begin. The dance of light. What are the northern lights? Picture this. You're standing in the Arctic darkness, miles from any city, on a night so cold your breath freezes in midair and falls as tiny ice crystals that sparkle in your flashlight beam. Above you, the stars shine with a clarity impossible in most places on Earth. So many stars that the Milky Way looks like a river of light flowing across the velvet black of space. And then, without warning, something begins to happen. A faint glow appears on the northern horizon. At first, you think it might be distant city lights, though you know there are no cities for hundreds of miles. Or perhaps dawn, even though dawn is hours away. But then the glow begins to move. It rises. It spreads. And suddenly, impossibly, the entire sky erupts into rivers of green light, flowing and pulsing like waves on some celestial ocean. The light moves with purpose, almost with intelligence. It forms curtains that billow and fold in an invisible wind. Arcs stretch from horizon to horizon, bright enough to cast your shadow on the snow. Spirals twist upward toward the zenith, spinning like cosmic tornadoes. And then, just when you think you've seen the full spectrum of what's possible, streaks of violet appear, then crimson, then a blue so deep and pure it seems to come from another dimension entirely. This is the aurora borealis, the northern lights. And what you're witnessing isn't just beautiful. It's a war, an invisible battle between the sun and earth that has been raging for billions of years. A battle that, during this solar maximum, is intensifying to levels we haven't seen in over 2 decades. Let's start where the story begins. The sun itself. The sun is not a gentle sphere of steady light. It's a roiling, seething ball of plasma where temperatures in the core reach 27 million degrees Fahrenheit. At these temperatures, hydrogen atoms are crushed together with such force that they fuse into helium, releasing energy that eventually makes its way to the surface and radiates out into space as light, heat, and something else. Something invisible, but profoundly important. The solar wind. Every second, the sun ejects about 1 million tons of matter into space. Think about that. 1 million tons. Every second. This torrent of particles, mostly electrons and protons, streams outward from the sun at speeds between 250 and 500 miles per second, creating a continuous flow we call the solar wind. It carries with it fragments of the sun's magnetic field, frozen into the plasma like magnetic fossils. But during solar maximum, when the sun's magnetic field is at its most chaotic, something more dramatic happens. Coronal mass ejections, or CMEs, giant clouds of magnetized plasma, billions of tons in mass, can erupt from the sun's surface and hurtle toward Earth at speeds of up to 3 million miles per hour. When one of these plasma clouds slams into Earth's magnetic field, that's when the real show begins. Here's where the story becomes both elegant and complex. Earth is surrounded by an invisible shield called the magnetosphere. This magnetic bubble, generated by swirling currents of liquid iron in Earth's core, extends tens of thousands of miles into space. It's not a perfect sphere. The solar wind compresses it on the day side, pushing it inward to about 40,000 miles above Earth's surface. On the night side, it stretches into a long tail that extends beyond the orbit of the Moon. When the solar wind hits this magnetosphere, most of it is deflected, forced to flow around Earth like water flowing around a stone in a stream. But not all of it. Some of the charged particles become trapped, caught in Earth's magnetic field like fish in an invisible net. They spiral along the magnetic field lines, bouncing back and forth between the northern and southern hemispheres. And as they approach the poles, where the magnetic field lines converge and dive down into the atmosphere, something magical happens. At altitudes between 60 and 200 miles above Earth's surface, these high-energy particles slam into atoms and molecules in our atmosphere, mostly oxygen atoms and nitrogen molecules. Each collision transfers energy, exciting these atoms to higher energy states. And when the atoms relax, returning to their normal states, they release that excess energy as light. Photons. Pure, visible radiance. But here's where something surprising was discovered recently, something that shows how much we still don't fully understand about even the most beautiful phenomena we observe. In 2021, a team of physicists at the University of Iowa published research in Nature Communications that finally proved the mechanism by which auroral electrons gain the tremendous speeds needed to create the brightest displays. They demonstrated that electrons literally surf on electromagnetic waves called Alfvén waves. Picture a surfer catching an ocean wave, being accelerated faster and faster as the wave carries them forward. That's essentially what happens, except instead of water, we're talking about waves in magnetized plasma, and instead of speeds of 20 or 30 miles per hour, we're talking about 45 million miles per hour. The electrons, moving at just the right speed relative to these plasma waves, are picked up and accelerated through a process called Landau damping. The physicist Lev Landau first theorized this mechanism in 1946, but it took until the 21st century, using a 60-foot-long plasma chamber at UCLA, for scientists to definitively prove it happens in nature. Even now, more than 160 years after Richard Carrington first connected solar activity to auroras, we're still discovering fundamental mechanisms behind the lights. The auroras we see are not random. They follow patterns governed by the physics of Earth's magnetic field. Because the magnetic field funnels charged particles toward the poles, auroras occur primarily in oval-shaped zones centered on the magnetic poles, not the geographic poles, but the magnetic ones, which are slightly offset. These auroral ovals shift and expand depending on solar activity. During quiet times, they remain confined to high latitudes, visible only from places like northern Canada, Alaska, Scandinavia, and Siberia. But during geomagnetic storms, something dramatic happens. The auroral oval can expand by thousands of miles, bringing auroras to regions that normally never see them. During the May 2024 Gannon storm, auroras were photographed as far south as Puerto Rico, at a latitude of 18 degrees north. To put that in perspective, that's farther south than Mumbai, Bangkok, or the southern tip of Mexico. People in the Caribbean, where snow never falls and winter is merely a less humid version of summer, saw the northern lights dancing above tropical palms. And this is just the beginning, because we're still in solar maximum. And based on what we understand about solar cycles, the strongest storms don't always occur at the peak. Sometimes they happen on the declining phase, when the sun's magnetic field is reorganizing itself after the flip that occurs at maximum. Which means the most spectacular auroral displays of this cycle might still be ahead of us. The shape and structure of auroras vary tremendously, and each form tells a different story about what's happening in the magnetosphere. Sometimes auroras appear as diffuse glows on the horizon, faint and greenish, easy to mistake for light pollution if you don't know what you're looking for. These represent quieter auroral activity, times when particles are trickling into the atmosphere at a steady rate. Other times they form distinct arcs, nearly straight lines of light stretching across the sky from east to west. These arcs mark the boundary of the auroral oval, the southern edge of the region where particles are currently entering the atmosphere. They can persist for hours, slowly shifting north or south as conditions in space change. During active periods, auroras transform into curtains or draperies, vertical structures that billow and wave like fabric in a breeze. These represent enhanced energy input, moments when bursts of particles are accelerating downward along magnetic field lines. The curtains can move incredibly fast, rippling across the sky in waves, each fold and shimmer representing changes in the flow of particles from space. Rayed arcs are even more dramatic. These structures show individual rays of light, like laser beams, shooting upward from a glowing arc. The rays are aligned with Earth's magnetic field lines, and when you see them, you're looking directly along the paths that individual groups of electrons traveled as they spiraled downward into the atmosphere. In a very real sense, you're seeing the magnetic field made visible. And then there are coronas, the rarest and most spectacular form. These occur when you're standing directly beneath the aurora, looking up at magnetic field lines that appear to radiate from a single point overhead, creating a circular pattern of light that seems to converge at the zenith. It's like looking up from beneath a dome made of light, with rays spreading out in all directions. During intense geomagnetic storms, coronas can fill the entire sky, pulsing and shifting with colors so vivid they seem almost unnatural. The aurora is not silent either. Here's something that surprised scientists for decades. For centuries, people have reported hearing the aurora, describing sounds like crackling, hissing, rustling like silk, or even something resembling soft clapping. These reports came from indigenous peoples across the Arctic, from Scandinavian observers, from Russian accounts. But scientists were skeptical. Auroras occur at altitudes of 60 to 200 miles, where the air is so thin it's essentially a vacuum. Sound waves can't travel through a vacuum. The physics seemed clear. Auroras should be silent. But the reports persisted. And in recent years, researchers have begun to take them seriously. Some now believe the sounds might be real, generated through a mechanism that's quite different from conventional sound transmission. One theory suggests that charged particles associated with auroras could create electrical discharges at ground level, similar to small lightning bolts but much quieter. Another proposes that very low-frequency electromagnetic waves generated by auroras could be converted to audible sound by certain materials, trees, buildings, even the observer's clothing, acting as natural antennas. The mystery isn't fully solved. But what seems increasingly clear is that people aren't imagining these sounds. They're hearing something real, even if we don't yet fully understand the mechanism. It's a reminder that even phenomena we've studied for over a century can still surprise us, still hold secrets we're only beginning to unlock. What creates the aurora at its core is elegant in its simplicity. Particles from the sun, guided by Earth's magnetic field, collide with our atmosphere and create light. But the details, the mechanisms, the intricate interplay of plasma physics and atomic excitation and electromagnetic wave propagation represent some of the most sophisticated science humans have ever undertaken. Every aurora is a reminder that we live in a universe governed by laws we're still working to fully understand. A universe where beauty and physics intertwine in ways that take our breath away. Where the same forces that create those shimmering curtains of light could, under slightly different circumstances, disable satellites, disrupt power grids, and remind us how fragile our technological civilization truly is. The northern lights are not just a light show, they're a connection, a thread linking us to the sun, to the cosmos, to forces that dwarf us in scale, but which we can nevertheless observe, measure, and comprehend. And right now, in 2025 and 2026, that connection is intensifying. The sun is waking up, the magnetic battle is escalating, and the auroras are responding with a fury we haven't seen in over 2 decades. The sun's heartbeat, understanding solar cycles. The sun, for all its apparent constancy, is not constant at all. It pulses, it breathes, it goes through cycles of activity and quiet that last roughly 11 years each, rising from a minimum to a maximum and then declining again in a rhythm as regular as a heartbeat. But here's something most people don't realize. This rhythm was hidden from us for most of human history. For thousands of years, across countless civilizations, the sun was simply the sun, unchanging, eternal, a perfect circle of light that rose each morning and set each evening with predictable regularity. The idea that it might have an internal cycle, that it might change in any meaningful way, would have seemed absurd. The discovery of the solar cycle is a story of patient observation, amateur dedication, and the gradual accumulation of data that finally revealed a pattern invisible to casual viewing. It begins with sunspots. In the early 17th century, as the telescope was turned skyward, for the first time, observers began to notice something peculiar. Dark spots on the sun's surface. Some were small, barely visible even through a telescope. Others were large enough that if you could safely look at the sun with the naked eye through thick fog or smoke, you might barely make them out without optical aid. Among the earliest systematic observers was Galileo Galilei, who documented sunspots beginning in 1610. His contemporary, German astronomer Johannes Fabricius published the first description of sunspots in June 1611. For a while, these spots were merely curiosities, interesting, but not obviously significant. Debates raged about what they were. Were they clouds in the sun's atmosphere? Small planets orbiting close to the solar surface? Imperfections that challenged the Aristotelian idea of celestial perfection? As decades turned to centuries, and as more and more observations accumulated, something became clear. The number of sunspots visible at any given time varied. Some years had many, others had few, but the variation seemed random, chaotic, without any discernible pattern. Until Samuel Heinrich Schwabe decided to count them, every single day, for decades. Schwabe was a German pharmacist and amateur astronomer living in the town of Dessau. Starting in 1826, he began systematically observing the sun every clear day, counting sunspots and carefully recording their numbers and positions. He was actually looking for something else entirely, a hypothetical planet inside Mercury's orbit called Vulcan, hoping to catch it transiting across the sun's disk. But what he found instead was far more interesting than a phantom planet. After 17 years of patient observation, in 1843, Schwabe announced his discovery. The number of sunspots on the sun's surface varied in a regular cycle lasting about 10 years. This was a revelation. The sun was not unchanging. It had an internal rhythm, a heartbeat. But here's the twist that makes this story so human and so scientific. Schwabe's initial announcement was largely ignored. He published his findings in a journal called Astronomische Nachrichten, but the astronomical community paid little attention. It wasn't until the renowned scientist Alexander von Humboldt included Schwabe's findings in Volume 3 of his monumental work Cosmos in 1851 that the discovery gained widespread recognition. Even then, skepticism remained, but other astronomers began to verify and extend Schwabe's work, and gradually, the reality of the solar cycle became undeniable. Swiss astronomer Rudolf Wolf refined the sunspot counting methodology and analyzed historical records going back centuries. He discovered that careful observers in previous eras had made sporadic sunspot observations that, when compiled, supported Schwabe's findings. Wolf created what we now call the Wolf sunspot number, a standardized measure of solar activity that accounts for both the number of sunspots and the number of sunspot groups visible on the solar disk. He determined that the average length of the solar cycle was actually closer to 11 years, and he numbered the cycles retroactively, establishing what we now call Cycle 1 as beginning in 1755. We're currently in Cycle 25, the 25th complete cycle since systematic observation began. But understanding that the solar cycle existed was only the beginning. The physical cause of the cycle remained a mystery for another century. It wasn't until the 20th century, with advances in understanding of plasma physics, magnetic fields, and the sun's internal structure, that scientists began to piece together the mechanism. Here's what we now understand, though even this picture is incomplete and continues to be refined. The solar cycle is fundamentally magnetic. Deep inside the sun, beneath the visible surface, is a region called the tachocline, a boundary layer between the sun's radiative interior and its convective outer envelope. In this region, differential rotation, the fact that the sun's equator rotates faster than its poles, stretches and twists the sun's magnetic field like a rubber band being wound tighter and tighter. Imagine taking a bundle of rubber bands and twisting them. At first, the bands remain fairly orderly, but as you continue twisting, they become increasingly tangled, kinked, and chaotic. Eventually, some of the bands might even snap, releasing their stored energy suddenly and violently. Something similar happens with the sun's magnetic field. As the field lines become increasingly twisted by differential rotation, they store more and more magnetic energy. Eventually, these magnetic field lines break through the sun's surface in complex loops and tangles, creating sunspots. Sunspots are regions where the magnetic field is so strong, typically thousands of times stronger than Earth's magnetic field, that it inhibits convection. Hot plasma that would normally rise to the surface is suppressed. The result is a region that's slightly cooler than its surroundings, typically around 6,500 degrees Fahrenheit compared to the surrounding 10,000 degrees. That temperature difference makes sunspots appear dark, though if you could see a sunspot by itself, it would still be blindingly bright, brighter than the full moon. At solar minimum, the sun has relatively few sunspots and is generally quiet. The magnetic field is fairly orderly, with distinct north and south magnetic poles, similar to Earth's magnetic field. Some solar minima are so deep that the sun can go for days or even weeks without a single visible sunspot. But as the cycle progresses toward solar maximum, the magnetic field becomes increasingly chaotic. Sunspots appear in greater numbers. Solar flares, sudden releases of magnetic energy that heat plasma to tens of millions of degrees and blast X-rays and other radiation into space, become more frequent and more powerful. Coronal mass ejections, those giant clouds of magnetized plasma we discussed earlier, erupt with increasing regularity. And then, at solar maximum, something remarkable happens. Something that seems almost impossible when you first hear about it. The sun's magnetic field flips completely. North becomes south. South becomes north. This isn't a gradual transition. Over the course of a few months, the sun's magnetic poles reverse polarity. And this flip, this fundamental reorganization of the sun's magnetic structure, marks the peak of the solar cycle. After the flip, As the cycle progresses toward the next minimum, sunspot activity gradually decreases. The magnetic field begins to organize itself again, growing more orderly. And the whole process prepares to repeat over and over in a cycle that has been ongoing for as long as the sun has existed. But here's something that should give you pause, something that reveals just how much we still don't understand about our own star. We don't know why the cycle lasts 11 years. Think about that. We've been observing the solar cycle for over 175 years. We've developed sophisticated models of the sun's interior. We've sent spacecraft to study the sun from multiple vantage points. We've mapped its magnetic field with exquisite precision. And yet we still can't predict the exact length of the cycle, which varies from as short as 9 years to as long as 13 years. We don't fully understand what determines the amplitude of each cycle, why some maxima are strong with hundreds of sunspots visible at peak, while others are weak with barely a few dozen. This brings us to solar cycle 25, and to one of the biggest surprises in solar physics in decades. When cycle 25 began in December 2019, scientists convened a solar cycle prediction panel, a group of experts from NASA, NOAA, and the International Space Weather Community, to forecast how strong the cycle would be. They looked at the previous cycle, cycle 24, which had been the weakest in a century, with a peak-smoothed sunspot number of just 116, well below the long-term average of 179. They considered various prediction methods, dynamo models, statistical techniques, and empirical relationships between cycles. And in December 2019, the panel issued its prediction. Solar cycle 25 would be weak, similar to cycle 24, peaking around July 2025 with a smoothed sunspot number of approximately 115. This prediction wasn't made carelessly. It was based on the best available science, peer-reviewed methods, and the combined expertise of dozens of solar physicists. Research papers were published detailing the rationale. Space agencies planned their missions accordingly. The message was clear: expect a quiet sun. Then reality intervened. By 2022, it was becoming clear that cycle 25 was not behaving as predicted. Sunspot numbers were consistently higher than forecast. Solar flares were occurring more frequently. In October 2023, NOAA issued a revised prediction, moving the expected peak earlier to between January and October 2024, and raising the forecast peak-smoothed sunspot number to between 137 and 173. Even this revised prediction underestimated what was coming. By August 2024, the smoothed sunspot number had reached 156.7, solidly in the middle of the revised forecast range. But that's just the smoothed number, which averages out fluctuations over time. The daily sunspot numbers were even more dramatic. On August 8, 2024, the daily sunspot number hit 229, a 23-year high. Then came the storms. In May 2024, active region AR36664, a complex sunspot group that grew to exceptional size, produced a barrage of X-class flares and multiple coronal mass ejections in rapid succession. When these CMEs slammed into Earth's magnetosphere on May 10 through 11, they triggered the first G5 geomagnetic storm in over 20 years. The auroras it created were visible as far south as the tropics. And as we've already discussed, the disruption to GPS systems cost American farmers over $500 million in a single weekend. On October 3, 2024, sunspot region AR3842 unleashed an X9.0 flare, the strongest of the entire cycle so far, and one of the most powerful solar flares ever recorded. It was so intense that it created radio blackouts on the sunlit side of Earth, disrupting high-frequency communications across multiple continents. And on October 15, 2024, came the official announcement: the Sun has reached solar maximum. But here's the twist, the reveal that makes this moment in solar history so remarkable. We don't actually know when the true peak occurred. Or rather, we won't know for several more months, possibly not until mid-2025 or later. Let me explain why. The smoothed sunspot number, the official measure used to define solar maximum, is calculated using a 13-month running average. That means to determine the value for any given month, you need data from the 6 months before and the 6 months after. It's only after you've passed the peak and tracked the decline for 6 months that you can definitively say that month, right there, was the maximum. What the October 2024 announcement really meant was this: based on current data and the pattern of activity over the past 2 years, we are now in the solar maximum period. The actual month of peak activity might have already occurred, or it might be several months in the future. We won't know until we have the benefit of hindsight. And there's something else, something that makes this even more interesting. NOAA's Space Weather Prediction Center has noted that peak geomagnetic activity often occurs not at solar maximum itself, but in the declining phase of the cycle, as the Sun's magnetic field reorganizes after the polarity flip. This suggests that the most intense geomagnetic storms, the events that produce the most spectacular auroras and pose the greatest risk to technology, might still be ahead of us. In other words, we're living through solar maximum right now. The May 2024 Gannon storm might not be the strongest event of this cycle. The October 2024 X9.0 flare might not be the most powerful eruption we'll see. The peak might still be coming. And that brings us to a question that matters deeply for anyone hoping to see auroras, for anyone concerned about space weather impacts, for anyone who simply wants to understand what's happening to our Sun. Why did Solar Cycle 25 surprise us? Why did every prediction, made by some of the world's leading experts, turn out to be wrong? The honest answer is, we're not entirely sure. But there are some intriguing possibilities, clues that suggest we might be missing something fundamental about how the solar dynamo operates. One hypothesis centers on the idea that the Sun's magnetic field might have a longer-term cycle overlying the 11-year cycle, a multi-decadal rhythm that modulates the strength of individual cycles. Some solar physicists have pointed out that a few prediction methods that incorporated these longer-term patterns actually came closer to accurately forecasting Cycle 25's strength. Another possibility is that Cycle 25's unexpected vigor might be connected to the unusual weakness of Cycle 24. Perhaps the Sun's dynamo, suppressed during the previous cycle, is now overcompensating, producing a stronger-than-expected rebound. Or it could be that our fundamental understanding of the solar dynamo, the mechanism that generates and sustains the Sun's magnetic field, is still incomplete. That despite decades of study, despite spacecraft observations and sophisticated computer models, we're still missing key pieces of the puzzle. What we do know is this: the Sun is more active than anyone predicted. Solar maximum is happening now, or has just recently occurred. And the implications of this, both for aurora viewing and for our technology-dependent civilization, are profound. The next year, possibly even the next 2 years, represent a window of opportunity, a time when the Sun is at or near its peak activity, when geomagnetic storms are frequent and intense, when auroras reach farther from the poles than they do during most years, and when, if we're paying attention, we might witness some of the most spectacular natural light shows any of us will ever see. But those same storms that create breathtaking auroras also pose risks, real risks to satellites, to power grids, to GPS systems, to all the infrastructure our modern world depends upon. To understand those risks, we need to journey deeper into the realm of space weather, into the invisible storms that rage in the space between Earth and Sun, into a realm where, just once in recorded history, a storm of such ferocity struck Earth that it set the very wires of human communication ablaze with auroral fire. The 2025-2026 solar maximum, a perfect storm of light. Right now, as you rest, the Sun is hosting a cosmic tempest. On its surface, sunspots cluster in groups, some of them larger than Jupiter, each one a tangled knot of magnetic field lines storing energy equivalent to billions of nuclear weapons. Above these sunspot groups, towering loops of plasma arch hundreds of thousands of miles into space, following magnetic field lines like iron filings near a bar magnet. And occasionally, without warning, those loops become unstable. They snap, they reconnect, and they unleash that stored energy in a fraction of a second. This is solar maximum in 2025 and 2026, and it's unlike anything we've experienced in over 2 decades. Let's put some numbers to what's happening, because the scale is almost incomprehensible. A typical X-class solar flare, the most powerful category in the standard classification system, releases energy equivalent to tens of millions of 100 megaton nuclear bombs exploding simultaneously. When sunspot region AR3842 produced that X9.0 flare on October 3, 2024, it released, in the space of just a few minutes, more energy than humanity has consumed in its entire history. The radiation from that single event traveled at the speed of light, reaching Earth in just over 8 minutes, where it ionized the upper atmosphere and created radio blackouts across Africa and parts of Europe. But flares, as powerful as they are, represent only one type of solar eruption. The real heavy hitters, the events that pose the greatest risk to Earth and create the most spectacular auroras, are coronal mass ejections. Imagine a bubble of plasma, typically weighing billions of tons, being ejected from the Sun's surface at speeds ranging from a few hundred miles per second to, in extreme cases, over 2,000 miles per second. This plasma cloud carries with it fragments of the Sun's magnetic field, frozen into the plasma by the physics of magnetohydrodynamics. As it travels through interplanetary space, it sweeps up the solar wind ahead of it, growing larger and more powerful. When one of these CMEs slams into Earth's magnetosphere, the collision creates a geomagnetic storm, and the strength of that storm depends on several factors: the speed of the CME, its mass, the strength of its embedded magnetic field, and critically, the orientation of that magnetic field relative to Earth's. Here's where physics becomes fate. If the magnetic field embedded in a CME is oriented northward, roughly aligned with Earth's magnetic field, the interaction is relatively gentle. The CME slides past, deflected by Earth's magnetic shield, causing only minor disturbances. But if the magnetic field is oriented southward, opposite to Earth's field, something remarkable happens. The two magnetic fields can reconnect, a process where field lines break and reform in a new configuration. This reconnection opens a gateway. Solar wind and CME plasma can pour directly into Earth's magnetosphere, injecting enormous amounts of energy. When this happens, when a fast, massive, southward-oriented CME collides with Earth, a major geomagnetic storm results. And during solar maximum, these perfect storm conditions occur far more frequently than during the quiet years of solar minimum. The May 2024 Gannon storm was exactly this kind of event. Multiple CMEs erupted from active region AR3664 over the course of several days. They merged in interplanetary space, a phenomenon called a cannibal CME, where faster clouds overtake and consume slower ones, creating a single, massive disturbance. When this combined storm front hit Earth on May 10th of 11, it carried a magnetic field that was not just southward oriented, but exceptionally strong. The numbers tell the story. The interplanetary magnetic field reached a magnitude of 73 nanotesla, with the southward component, the part that matters most for geomagnetic storms, reaching 56 NT. To put that in perspective, typical values hover around 5 to 10 NT. The solar wind speed peaked between 750 and 950 kilometers per second, and the resulting geomagnetic storm achieved a KP index of 9, the highest possible value on the planetary geomagnetic activity scale. It was classified as a G5 storm. Extreme, the first such classification in over 20 years. The previous G5 storm had occurred during the Halloween events of October 2003, and before that, during the Great March 1989 storm that famously knocked out power across Quebec. The Disturbance Storm Time Index, or DST, which measures the intensity of the ring current flowing around Earth during geomagnetic storms, dropped to 412 nanotesla during the peak of the Gannon storm. That's the largest negative DST value recorded for any G5 storm since 1989. And yet, despite its intensity, the Gannon storm didn't cause the catastrophic damage that many had feared. Power grids remained largely operational. Satellites experienced some anomalies, but no major failures. The most significant impact, ironically, was to GPS systems, a vulnerability that had been predicted but never tested at this scale until that weekend in May. This raises an interesting question, one that scientists are still actively investigating. Was the Gannon storm relatively benign because we were lucky? Or because our infrastructure, hardened and improved after past storms, is now more resilient than it was in 1989 or 2003? The answer seems to be both, with an emphasis on the luck part. Power companies, particularly in North America, had been warned days in advance that a major storm was coming. NOAA's Space Weather Prediction Center issued a G4 watch, then upgraded it to G5, giving utilities time to prepare. Some took preventive measures, reducing load on critical transformers, positioning repair crews, monitoring their systems closely. When the storm hit, they were ready, able to respond quickly to voltage fluctuations and prevent cascading failures. But there's also evidence that the Gannon storm, while intense, wasn't quite as geo-effective as it could have been. The term geo-effective refers to how efficiently a solar storm couples its energy into Earth's magnetosphere. Two storms with similar speeds and magnetic field strengths can have very different impacts depending on factors like the exact geometry of the collision, the duration of the southward magnetic field, and whether the CME hits Earth head-on or delivers a glancing blow. The Gannon storm was nearly head-on, but it could have been even more direct. The southward magnetic field, while strong, didn't maintain its maximum strength for as long as it might have. In other words, we got lucky. And that luck is unlikely to hold indefinitely. Since the Gannon storm in May 2024, solar activity has remained elevated. In the months following, numerous M-class and X-class flares erupted from various active regions. Additional G3 and G4 geomagnetic storms occurred, creating auroral displays visible at mid-latitudes. And that X9.0 flare in October, while it didn't produce a strongly Earth-directed CME, demonstrated that the Sun remains capable of exceptional violence. As we move through 2025 and into 2026, the expectation is for continued high activity. But here's the subtlety that many people miss. Solar maximum is not a single peak, but a plateau. A period typically lasting about 2 years, during which the Sun maintains elevated activity levels with frequent flares, regular CMEs, and persistent sunspot groups. Within that plateau, activity fluctuates. Some months see intense storms, others are relatively quiet. The variability makes prediction challenging. We know that over the next year, major geomagnetic storms are likely. We know that auroras will be visible at lower latitudes more frequently than usual. But predicting exactly when the next G4 or G5 storm will occur, which sunspot region will produce the next major flare, that remains beyond our current capabilities. What we can say with confidence is this: the window is open. For aurora chasers, for photographers, for anyone who's ever wanted to see the northern lights dancing across the sky, the next 12 to 18 months represent the best opportunity in over 20 years. But that same window represents a period of elevated risk for our technological infrastructure. And to understand that risk, we need to delve into the hidden world of space weather impacts, into the ways that storms on the sun can cascade through systems here on Earth in surprising and sometimes catastrophic ways. We need to talk about what happens when the invisible war between sun and Earth spills over into the realm of human technology. Solar storms and space weather, when the sun strikes back. On March 13, 1989, at 2:44 in the morning, the lights went out across the entire province of Quebec, Canada. 6 million people were plunged into darkness. Hospitals switched to emergency generators. Traffic lights failed. Heating systems shut down in the middle of a Canadian winter. And for 9 hours, one of North America's most developed regions functioned without electrical power. The cause? A geomagnetic storm triggered by a coronal mass ejection that had erupted from the sun 3 days earlier. But the mechanism by which a solar eruption 93 million miles away could switch off the lights for millions of people is more interesting and more concerning than most people realize. Let's trace the chain of events, because understanding this is key to understanding why space weather matters in an age of ubiquitous technology. When a CME slams into Earth's magnetosphere, it doesn't directly affect things on the ground. The magnetosphere shields us. But what it can't shield against are the secondary effects, the invisible waves of electromagnetic disturbance that ripple through Earth's magnetic field during a geomagnetic storm. As the magnetosphere shudders and convulses under the impact of solar plasma, Earth's magnetic field itself begins to fluctuate. And according to Faraday's law of electromagnetic induction, any conductor in a changing magnetic field will have electric currents induced in it. This is the basic principle behind electric generators and transformers. But during a geomagnetic storm, the entire surface of Earth becomes immersed in a massive, fluctuating magnetic field. Long-distance electrical transmission lines, stretching for hundreds of miles across the landscape, act as perfect antennas for these geomagnetically induced currents, or GICs. The currents, typically on the order of tens to hundreds of amperes, flow into the power grid through the grounded neutral points of transformers. Now, here's the problem. Power grid transformers are designed to handle alternating current at specific frequencies, typically 50 or 60 Hz. GICs are quasi-DC, direct current or very low frequency, alternating current. When DC current flows through a transformer designed for AC, it can cause something called half-cycle saturation. The transformer's magnetic core becomes saturated during half of each AC cycle, causing the transformer to draw excessive reactive power and heat up dramatically. One overheated transformer might trip offline as a protective measure. But if multiple transformers across a grid trip simultaneously, the load has to be redistributed instantly to remaining transformers, which may themselves be operating at or near their limits. The result can be a cascading failure, where one transformer trip leads to another, which leads to another, until large sections of the grid collapse. This is exactly what happened in Quebec in 1989. The combination of Quebec's geology, particularly the presence of conductive rocks that facilitated GIC flow, and the configuration of the power grid made the province especially vulnerable. When the geomagnetic storm hit, GICs flowed through the system, causing transformers to overheat and trip. The cascade took just 90 seconds from the first trip to total blackout. The blackout lasted 9 hours, but the vulnerability it exposed is permanent. And it's not limited to Quebec. A 2017 report commissioned by NOAA estimated that space weather disruptions to the electric power industry could result in losses ranging from $111 million for minor geomagnetic disturbances to as much as $27 billion for severe storms like the Quebec event. But those numbers might actually underestimate the risk, because they don't account for what would happen if a truly extreme storm, something on the scale of the 1859 Carrington event, were to strike today. Let's talk about the Carrington event, because it remains the benchmark, the nightmare scenario that space weather experts worry about. On September 1, 1859, British amateur astronomer Richard Carrington was in his private observatory, sketching sunspots as he did every clear day. Just before noon, he noticed something extraordinary. 2 intensely bright patches of white light suddenly appeared in a large sunspot group. They brightened over the course of about 5 minutes, then faded. Carrington had just witnessed and documented the first solar flare ever recorded. What he didn't know, couldn't have known with the technology of 1859, was that this flare was associated with a massive coronal mass ejection, one of the most powerful in recorded history. The CME, traveling at exceptionally high speed, possibly accelerated by a previous CME that had cleared the interplanetary medium of slower solar wind, reached Earth in just 17.6 hours. Typical CME transit times are 2 to 4 days. This one made the journey in less than a day. When it hit, the results were spectacular and terrifying in equal measure. Auroras were seen as far south as the Caribbean and Hawaii in the northern hemisphere, and as far north as Chile and Colombia in the southern hemisphere. The auroras were so bright that people in the Rocky Mountains woke up thinking it was dawn and began preparing breakfast. In parts of the northeastern United States, people reported being able to read newspapers by the light of the aurora at midnight. But the real drama played out in the telegraph systems, the only widespread electrical technology of the era. Telegraph operators across Europe and North America reported that their systems were going haywire. Some operators received electric shocks when they touched their equipment. Telegraph papers caught fire. Pylons threw sparks. And in what might be the most remarkable anecdote from the event, some telegraph operators discovered they could disconnect their batteries entirely and continue sending messages using only the current induced by the geomagnetic storm. One such exchange, documented in the Boston Evening Traveler, captures the surreal nature of the event. Boston operator to Portland operator. Please cut off your battery entirely for 15 minutes. Portland operator. Will do so. It is now disconnected. Boston. Mine is disconnected, and we are working with the auroral current. How do you receive my writing? Portland. Better than with our batteries on. Current comes and goes gradually. They continued exchanging messages for over 2 hours using only the current, induced by the geomagnetic storm, an unintentional demonstration of electromagnetic induction on a continental scale. Today, a Carrington-class event would be far more devastating, not because the storm itself would be different, but because our dependence on electrical and electronic systems has increased exponentially. Estimates of the economic impact of a Carrington-level storm striking today range from $600 billion to $2.6 trillion in the United States alone. That's equivalent to roughly 3 to 15% of annual GDP, making it potentially more costly than any natural disaster in American history. But the cost wouldn't be purely economic. A major geomagnetic storm could affect nearly every aspect of modern life. Satellites would be among the first casualties. The Earth's upper atmosphere heats and expands during geomagnetic storms, increasing atmospheric drag on satellites in low Earth orbit. This can cause satellites to lose altitude faster than expected, potentially leading to unplanned re-entry. In February 2022, a relatively minor G1 geomagnetic storm caused 38 of 49 SpaceX Starlink satellites to re-enter Earth's atmosphere prematurely, a loss of over $50 million worth of hardware. More directly, the charged particles and radiation associated with major solar storms can damage satellite electronics, corrupt data, and interfere with operations. During the May 2024 Gannon storm, numerous satellites reported anomalies. Some entered safe mode, temporarily suspending operations to protect their systems. Others experienced data corruption or instrument malfunctions. In a worst-case scenario, during a Carrington-class event, hundreds or thousands of satellites could be damaged or destroyed, effectively crippling global satellite communications, GPS, weather forecasting, and countless other services we've come to depend on. GPS systems, as the May 2024 experience demonstrated, are particularly vulnerable, and the implications extend far beyond farmers being unable to plant in straight lines. Commercial aviation relies heavily on GPS for navigation, especially during landing in low visibility conditions. Ships at sea use Jeeps for navigation, collision avoidance, and synchronization of shipping schedules. Financial systems use GPS timestamps to synchronize transactions across global markets. Even your smartphone depends on Jeeps not just for navigation, but for timing signals that coordinate cellular networks. During a major geomagnetic storm, Jeep can become unreliable or fail entirely. Position errors can grow from the usual few meters to hundreds of feet, making the system useless for precision applications. Timing errors can cascade through systems in unexpected ways. And in the May 2024 storm, this wasn't theoretical. It was real, measured, documented. GPS receivers were off by up to 230 feet for hours, and the effects persisted for up to 2 days in some regions. Radio communications, particularly high-frequency, HF radio, are also vulnerable. Airlines flying polar routes, where satellite communication coverage is sparse, depend on HF radio for communication with air traffic control. Ships at sea use HF radio as a backup when other systems fail. And numerous emergency services still rely on HF radio for long-distance communication. During solar flares, especially X-class flares, the intense X-ray and extreme ultraviolet radiation ionizes the D layer of Earth's ionosphere, the lowest layer, increasing its density dramatically. This enhanced D layer absorbs HF radio waves, preventing them from propagating long distances. The result, called a radio blackout, can last from minutes to hours. During the October 2024 X9.0 flare, radio blackouts affected Africa and parts of Europe, with some frequencies completely unusable on the sunlit side of Earth. Astronauts in space face direct radiation hazards during major solar storms. The International Space Station, orbiting at an altitude of about 250 miles, is still partially protected by Earth's magnetosphere. But during intense solar storms, astronauts may need to shelter in more heavily shielded areas of the station. For future missions to the Moon or Mars, where astronauts will be exposed to the full brunt of solar radiation without Earth's protective magnetic field, space weather forecasting becomes a life or death necessity. But perhaps the most insidious aspect of space weather is how interconnected our systems have become. A disruption in one area can cascade into others in unexpected ways. GPS failures affect precision agriculture, but they also affect timing in financial systems. Power grid failures don't just turn off lights. They disable cooling systems for nuclear reactors, shut down water treatment plants, and interrupt the supply chains that deliver food and medicine. After the May 2024 Gannon storm, researchers began to more fully appreciate these hidden vulnerabilities. The $500+ million loss in agriculture wasn't just from crops not being planted. It was from delays that pushed planting past optimal windows, reducing projected yields. It was from farmers having to choose between continuing to plant without GPS's guidance, risking misaligned harvesting later, or stopping work entirely, losing crucial days in a planting season measured in weeks. And this was just a G5 storm, intense but not unprecedented. A Carrington-class event could be several times stronger, with impacts that might take months or years to fully recover from. So what are we doing about it? The answer is more than we used to, but perhaps not enough. Space weather forecasting has improved dramatically over the past few decades. NOAA's Space Weather Prediction Center, located in Boulder, Colorado, operates 24 hours a day, 7 days a week, monitoring the sun and issuing forecasts and warnings when significant space weather events are expected. They have access to data from numerous spacecraft, including the Solar Dynamics Observatory, SDO, which continuously images the sun in multiple wavelengths, and the Deep Space Climate Observatory, DSECOVR, positioned at the L1 Lagrange point about 1 million miles from Earth, which provides advance warning of incoming CMEs typically 15 to 60 minutes before they hit Earth. That warning time, while better than nothing, is barely enough for power companies to implement protective measures, for satellite operators to put their spacecraft into safe mode, or for airlines to reroute flights away from polar regions where radio blackouts and radiation exposure are most severe. The holy grail of space weather forecasting would be to predict, days in advance, not just that a CME is headed toward Earth, but exactly how strong the resulting geomagnetic storm will be. This requires understanding the magnetic field structure inside the CME, information we can only measure directly once the CME reaches spacecraft near Earth, by which point it's too late for meaningful preparation. Some researchers are working on techniques to infer CME magnetic field orientation from observations of the eruption on the Sun. Others are developing improved models of CME propagation through interplanetary space. But as the May 2024 Gannon storm demonstrated, we're still far from perfect predictions. The storm was forecast, but its intensity and duration exceeded expectations. New spacecraft missions are in the works that might improve our forecasting capabilities. NASA's Parker Solar Probe, which has been diving closer to the Sun than any spacecraft in history, is gathering data on solar wind acceleration and CME formation that could improve models. The European Space Agency's Solar Orbiter is viewing the Sun from angles impossible to achieve from Earth, potentially providing better warning of CMEs forming on the far side of the Sun that will eventually rotate into Earth-facing positions. And in September 2025, NOAA plans to launch the Space Weather Follow-on Lagrange 1 SWFO-1 mission, which will replace the aging DSECOVR spacecraft and provide improved instruments for measuring the solar wind and magnetic field of incoming CMEs. But even with improved forecasting, the fundamental challenge remains. We've built a technological civilization that depends on systems vulnerable to space weather, and the Sun, indifferent to our dependence, continues its cycle of activity, occasionally unleashing storms that remind us how fragile our infrastructure truly is. The May 2024 Gannon storm was a warning. The October 2024 X9.0 flare was a demonstration of the Sun's power, and the continued high activity throughout 2025 and 2026 ensures that we'll have more opportunities, wanted or not, to test our resilience. But space weather isn't just about risk. It's also about wonder, about understanding our place in a dynamic cosmos, about appreciating the invisible forces that shape not just our skies, but our technological civilization. And to truly appreciate those forces, we need to understand the invisible shield that protects us, the remarkable magnetic bubble that makes Earth habitable in a universe filled with radiation and charged particles. We need to explore the magnetosphere, Earth's magnetic shield, our invisible protector. Imagine Earth without its magnetic field, without the invisible bubble that surrounds our planet, deflecting solar wind and shielding us from cosmic radiation. What would happen? The answer is sobering. We'd look like Mars. Mars once had a magnetic field, evidence preserved in the magnetization of ancient Martian rocks. But around 4 billion years ago, for reasons we're still trying to fully understand, Mars's magnetic field shut down. Without its protective shield, the planet was exposed directly to the solar wind. Over millions of years, that wind stripped away most of Mars's atmosphere. What was once a world with liquid water on its surface, possibly even life, became the cold, dry, barren desert we see today. Earth's magnetic field isn't just a curiosity. It's a fundamental prerequisite for habitability. Without it, we wouldn't exist. But what exactly is the magnetosphere? How does it work? And how does it interact with the solar wind and CMEs to create both the auroras we admire and the geomagnetic storms we've learned to fear? The story begins deep inside Earth, nearly 2,000 miles below your feet. Earth's core consists of two parts. The inner core is solid, a sphere of iron and nickel about 1,500 miles in diameter, heated to temperatures rivaling the surface of the Sun. Surrounding this is the outer core, about 1,400 miles thick, composed of liquid iron alloyed with lighter elements. This liquid metal is in constant motion, driven by heat escaping from the core and by Earth's rotation. And here's where the magic happens. Moving, electrically conductive fluid, in this case liquid iron, can generate magnetic fields through a process called the dynamo effect. It's the same principle that makes an electric generator work, except instead of spinning a coil of wire inside a magnetic field, Earth is spinning churning liquid metal that generates its own magnetic field. The field lines emerge from near Earth's south magnetic pole, loop outward through space, and return near the north magnetic pole. If Earth were alone in space, these field lines would form a symmetric pattern, like the field around a bar magnet. But Earth isn't alone. It's immersed in the solar wind, that constant flow of charged particles from the Sun. And when the solar wind encounters Earth's magnetic field, it compresses it, distorts it, shapes it into something far more complex and dynamic. On the day side, facing the Sun, the solar wind pushes against Earth's magnetic field, compressing it inward. The distance to the magnetopause, the boundary between Earth's magnetic field and the solar wind, varies depending on the pressure of the solar wind, but it's typically around 40,000 miles above Earth's surface. About 6 asteroids, Earth radii from the center of the planet. On the night side, away from the Sun, the magnetic field is stretched into a long tail called the magnetotail, which extends far beyond the orbit of the Moon, potentially millions of miles into space. This tail contains two lobes, one with field lines pointing toward Earth and one with field lines pointing away, separated by a neutral sheet where the magnetic field is weak. The magnetosphere isn't a solid boundary. It's a dynamic, constantly shifting region where Earth's magnetic field and the solar wind compete for dominance. Most of the solar wind is deflected, forced to flow around the magnetosphere like water flowing around a rock. But some particles become trapped, caught in Earth's magnetic field and confined to specific regions. The most famous of these regions are the Van Allen radiation belts, discovered in 1958 by James Van Allen using data from Explorer 1, the first American satellite. These belts are toroidal, donut-shaped regions filled with high-energy charged particles, mostly protons and electrons, trapped by Earth's magnetic field and spiraling back and forth between the northern and southern hemispheres. There are two main Van Allen belts. The inner belt, centered about 2,000 to 3,000 miles above Earth's surface, contains primarily high-energy protons. The outer belt, located between about 8,000 and 36,000 miles altitude, contains primarily electrons. These belts pose a significant radiation hazard to satellites and astronauts. Spacecraft designed for long-term operation in these regions, like GPS satellites, which orbit at about 12,000 miles, need extensive radiation shielding to survive. During geomagnetic storms, the structure of the magnetosphere changes dramatically. The magnetopause can be pushed inward, sometimes as close as 25,000 miles from Earth. The outer Van Allen belt becomes more populated with energetic electrons, and in the magnetotail, something remarkable happens. As the solar wind and CME plasma press against the magnetosphere, they can cause magnetic field lines from opposite sides of the magnetotail to be pushed together. When these oppositely directed field lines meet, they can reconnect, a process where the field lines break and reform in a new configuration, converting magnetic energy into kinetic energy. This process accelerates particles to tremendous speeds, sending them shooting down toward Earth along magnetic field lines that lead to the polar regions. This is magnetic reconnection, and it's one of the most important processes in space plasma physics. It's what allows solar wind energy to enter the magnetosphere. It's what accelerates particles to the speeds needed to create bright auroras. And it's still not fully understood, even after decades of study. What makes the magnetosphere so complex is that it's not static. It breathes, pulsing in and out in response to variations in the solar wind. It has wave-like disturbances that propagate through it. It has regions where plasma is hot and others where it's cold, areas of strong magnetic field and areas of weak field, all constantly shifting and changing. One of the most dynamic regions is the magnetotail. This is where substorms occur, sudden releases of energy that last from 1 to 2 hours and are a major component of geomagnetic storms. During a substorm, magnetic energy that has been stored in the magnetotail is suddenly released, accelerating particles and creating bright auroral displays that can ripple across the sky in minutes. The magnetosphere also interacts with Earth's atmosphere in complex ways. At altitudes of 60 to 600 miles, we find the ionosphere, a layer of the atmosphere where solar radiation has ionized gas molecules, creating a region of plasma. The ionosphere and magnetosphere are coupled, connected by electric currents and electromagnetic forces. Changes in one can drive changes in the other. And here's something many people don't realize. The magnetic field itself is not perfectly aligned with Earth's rotation axis. The North Magnetic Pole, the point where magnetic field lines point straight down into the Earth, is currently located in the Arctic Ocean, hundreds of miles from the geographic North Pole. And it's moving, drifting northward at a rate of about 30 miles per year, faster than at any time in recent history. Even more remarkably, the magnetic field completely reverses polarity on geological timescales, though irregularly. The last reversal occurred about 780,000 years ago. When these reversals happen, the North Magnetic Pole becomes the South Magnetic Pole, and vice versa. The process takes thousands of years, during which the field becomes more complex and possibly weakened, potentially allowing more cosmic radiation to reach Earth's surface. But that's a slow process, operating on timescales far longer than human civilizations. On human timescales, the challenge isn't the slow drift of the magnetic poles or the distant possibility of a geomagnetic reversal. It's the hour-to-hour, day-to-day variations driven by space weather. During a major geomagnetic storm, the magnetosphere is compressed, its structure altered, its currents intensified. These changes create the geomagnetically induced currents that threaten power grids. They enhance the Van Allen belts, increasing radiation hazards for satellites. They heat the upper atmosphere, increasing drag on low-orbit spacecraft. And they funnel enormous numbers of high-energy particles into the polar regions, creating the auroras that light up the sky. Understanding the magnetosphere, modeling its behavior, predicting how it will respond to solar storms, these remain active areas of research. NASA and other space agencies have flown numerous missions, like the Themis, Time History of Events and Macroscale Interactions during substorms, Constellation, and the Magnetospheric Multiscale (MMMS) mission, specifically designed to study magnetospheric physics. These missions have revealed a magnetosphere even more complex and dynamic than earlier models suggested. They've captured magnetic reconnection in action, measuring how it accelerates particles and converts energy. They've tracked the formation and evolution of substorms. They've mapped the three-dimensional structure of the Van Allen belts and how they change during geomagnetic storms. And yet, despite this progress, prediction remains challenging. The magnetosphere is a non-linear system, meaning small changes in initial conditions can lead to large changes in outcomes. This makes forecasting the exact strength and timing of geomagnetic effects difficult, even when we know a CME is on its way. What we do know is that Earth's magnetic field is our first line of defense against the hazards of space weather. Without it, the charged particles from solar storms would penetrate directly into our atmosphere, damaging the ozone layer, irradiating the surface, and making complex life on land nearly impossible. The magnetosphere doesn't eliminate the dangers of space weather, but it mitigates them, deflecting most of the solar wind, confining the most intense effects to the polar regions, and giving us a chance to protect our technology when we know a storm is coming. It's an invisible shield, yes, but it's also a dynamic, breathing, evolving structure, one that responds to every gust of the solar wind, every surge of a CME, every fluctuation in space weather. And right now, during solar maximum 2025 to 2026, that shield is being tested more frequently and more severely than it has been in over 2 decades. Every aurora is a sign of that test. Every geomagnetic storm, whether minor or severe, is a reminder of the ongoing battle between Earth and Sun. And every night that the auroral oval expands southward, bringing those shimmering curtains of light to latitudes that rarely see them, is an invitation. An invitation to witness, firsthand, the invisible war made visible. An invitation to see our planet's shield at work, glowing with the energy of particles that, if not for that magnetic bubble, would make Earth's surface as lifeless as the Martian plains. The science of aurora colors. Painting with atoms, auroras are painted in light, but not all light is the same. The shimmering greens, the deep reds, the rare violets and blues, each color tells a story. A story about altitude, about atmospheric composition, about the energy of incoming particles, and the physics of atomic excitation. Understanding aurora colors is understanding how energy, particles, and atoms interact to create one of nature's most beautiful displays. Let's start with the most common color, the one that dominates most auroral displays: green. That brilliant, luminous green that looks almost artificial in its intensity, like a neon sign stretched across the sky, comes from oxygen atoms. Specifically, it comes from oxygen atoms at altitudes of roughly 60 to 150 miles above Earth's surface. When a high-energy electron collides with an oxygen atom, it can knock one of the atom's electrons to a higher energy level, what physicists call an excited state. The atom doesn't stay excited for long. After about 3/4 of a second, the electron drops back to its ground state, and when it does, it releases the energy difference as a photon, a particle of light. For oxygen atoms, that particular electronic transition produces light with a wavelength of 557.7 nanometers, which our eyes perceive as yellowish-green. This is by far the brightest and most common auroral emission. But here's something interesting. That 3/4 of a second relaxation time might seem short, but in the context of the upper atmosphere, it's actually quite long. At the altitudes where green auroras occur, the atmosphere is thin but not absent. If an excited oxygen atom collides with another or molecule before it has a chance to emit its photon, the excitation energy can be transferred through the collision rather than being released as light. This process, called collisional quenching, limits where and how brightly different auroral colors can appear. At lower altitudes, where the atmosphere is denser and collisions are more frequent, collisional quenching suppresses emissions with long relaxation times. This is why you don't see certain aurora colors at low altitudes, even though the right atoms are present and being excited by incoming particles. Now let's talk about red auroras, which are rarer and often require more intense geomagnetic activity to produce. Red auroras also come from oxygen atoms, but from a different electronic transition. When oxygen atoms are excited to an even higher energy level, they can emit light at 630 nanometers, which appears as a deep, blood-red color. This transition has an even longer relaxation time, about 110 seconds. That's nearly 2 minutes. Because of this long relaxation time, collisional quenching prevents red oxygen emissions at lower altitudes. Red auroras only appear at altitudes above about 150 miles, where the atmosphere is thin enough that atoms can remain excited for minutes without colliding with anything. During the most intense geomagnetic storms, when high-energy particles penetrate deep into the atmosphere, you can sometimes see red auroras extending down to lower altitudes, mixing with green to create orange or yellow hues. And occasionally, during exceptional storms, pure red auroras can dominate the entire sky, creating displays so dramatic that historical observers described the sky as appearing to be on fire. The March 1989 Quebec storm produced extensive red auroras visible across much of North America. Historical accounts of the 1859 Carrington event describe auroras so red and intense that people thought distant cities were burning. During the May 2024 Gannon storm, red auroras were photographed from numerous locations at mid to low latitudes, with some observers reporting that the red was so vivid it appeared artificial, like something illuminated by stage lights rather than natural atmospheric processes. Blue and purple auroras are less common but strikingly beautiful when they occur. These colors come primarily from ionized nitrogen molecules. The ionized part is important. Neutral nitrogen molecules emit different colors than ionized ones. When a nitrogen molecule loses an electron, becoming ionized, and then recombines with a free electron, it can emit blue light around 428 nanometers or red-violet light at longer wavelengths. Blue emissions tend to appear at the lower edges of auroral displays, often fringing the bottom of green curtains. They're most visible during very active auroras when particles are penetrating deeper into the atmosphere. Neutral nitrogen molecules, when excited by particle collisions, can produce emissions at various wavelengths, including parts of the spectrum that appear deep red or violet to our eyes. These emissions contribute to the complex color palette visible during intense auroral displays, but are generally fainter than the oxygen emissions. One of the fascinating things about auroral colors is how they appear different to cameras than to the human eye. Many auroras that appear white or pale green to the naked eye show vivid reds, purples, and other colors in long exposure photographs. This happens for two reasons. First, the human eye has two types of light-sensitive cells: rods, which are very sensitive but see only in black and white, and cones, which see color but require more light to function. During auroras, especially fainter ones, your rods are doing most of the work. You see the aurora, you see its structure and motion, but the colors appear muted or absent because there isn't enough light to fully activate your color-sensing cones. Cameras, with their ability to integrate light over seconds or even minutes, can capture colors that are present but too faint for our eyes to register under low-light conditions. This is why aurora photographs often look more colorful than what observers saw with the naked eye. It's not that the photos are fake or enhanced, though some certainly are. It's that the camera is seeing and recording colors that were there all along, but were below the threshold for human color vision. Second, human color perception is adapted to daylight conditions. Our eyes are most sensitive to green and yellow wavelengths, which is why green auroras often appear brightest even when other colors are present in similar physical intensity. Cameras, especially modern digital sensors, can be more uniformly sensitive across the visible spectrum, capturing reds and blues that our eyes tend to underperceive. But here's something that brings us back to the current solar maximum. The intensity and color of auroras depend directly on how much energy the incoming particles carry and how many particles are arriving. During major geomagnetic storms like the May 2024 Gannon storm, the flux of high-energy particles increases dramatically. More particles means brighter auroras. Higher energy particles means penetration to lower altitudes and excitation of more varied atomic and molecular transitions, producing a richer spectrum of colors. This is why the auroras during solar maximum are not just more frequent, they're more colorful, more intense, more likely to display the full spectrum of possible emissions. During solar minimum, most auroras are faint and green, visible only near the poles. During solar maximum, especially during major storms, auroras can be bright enough to cast shadows, with multiple colors visible simultaneously, creating displays so complex and beautiful that they seem almost too perfect to be natural phenomena. There's also a temporal aspect to aurora colors that's easy to miss in still photographs. Auroral colors can change rapidly as the energy and type of incoming particles vary. A green aurora might suddenly flare with red as a burst of higher energy particles arrives. Blue fringes might appear and disappear as particle energies shift. During dynamic auroral displays, the interplay of colors can be as mesmerizing as the motion of the forms themselves. And then there's the question of spectrum lines that aren't visible to the human eye at all. Auroras emit not just in visible light, but also in ultraviolet and infrared wavelengths. Space-based instruments can observe these emissions, providing additional information about atmospheric composition and particle energies. Some of the most scientifically valuable data about auroras comes from wavelengths we could never see directly, even with the darkest skies and the most powerful geomagnetic storm. What all of this means is that every aurora is unique. The specific colors visible at any given moment depend on the altitude structure of the aurora, the energy spectrum of incoming particles, the viewing angle, atmospheric conditions, and even the sensitivity and dark adaptation of the observer's eyes. Two people standing 100 feet apart during the same auroral display might describe different colors, and both would be correct. One might be seeing blue fringes that the other misses. One might have better dark adapted vision, seeing reds that appear white to the other. Position relative to the auroral forms matters too. An aurora that appears green when viewed from the south might show blue edges when viewed from a different angle. This variability, far from being a problem, is part of what makes aurora viewing so compelling. Every display is different. Every night brings new colors, new combinations, new surprises. During this solar maximum, with enhanced activity creating more frequent and more intense auroras, observers at mid-latitudes who might see auroras once or twice are being treated to displays that previous generations might have had to travel to the Arctic to witness. And understanding what creates those colors, knowing that you're watching quantum mechanics and atomic physics playing out on a scale of hundreds of miles, somehow makes the experience even more profound. You're not just seeing pretty lights. You're watching atoms in Earth's upper atmosphere absorb energy from particles that left the sun days earlier, traveled 93 million miles through space, navigated Earth's magnetic field, and finally deposited their energy in a flash of color visible to the naked eye. You're seeing energy transformed, matter excited, photons created. You're witnessing the fundamental processes of physics that govern the universe, made visible and beautiful against the darkness of night. And during this solar maximum, those processes are operating at full intensity, painting the sky with a palette richer and more varied than any human artist could match. Auroras around the world, lights beyond Earth. When we talk about auroras, we usually mean the northern lights, the aurora borealis. But auroras are not unique to Earth's northern regions. They occur in the south too, mirroring their northern counterparts in what's called the aurora australis, the southern lights. And they're not even unique to Earth. Auroras have been observed on other planets in our solar system, revealing that the interaction between magnetic fields and charged particles is a universal phenomenon, playing out across the cosmos wherever the conditions are right. Let's start close to home, with the southern lights. The aurora australis is in every meaningful way identical to its northern twin. It's created by the same process, charged particles from the sun funneling into Earth's atmosphere along magnetic field lines that converge at the magnetic poles. The colors are the same, the physics is the same, even the shape and structure are remarkably similar. When satellites image both poles simultaneously from space, the auroral ovals often appear nearly mirror images of each other, though not perfectly so due to asymmetries in Earth's magnetic field and variations in the solar wind. What makes the southern lights less famous than their northern counterparts is purely geographical. The southern auroral oval is centered over Antarctica and the Southern Ocean. There are very few places on Earth where you can easily view the aurora australis. Southern Argentina and Chile, the southern tip of New Zealand, Tasmania, and occasionally southern Australia during major geomagnetic storms, these are about the only populated regions regularly graced by southern lights. But for those who do venture south, or for researchers stationed at Antarctic bases, the southern lights are just as spectacular as the northern ones. During the May 2024 Gannon storm, auroras were photographed from Chile, Argentina, New Zealand, and even as far north as Sydney, Australia, demonstrating that major geomagnetic storms can bring auroral displays to latitudes that rarely experience them in either hemisphere. Now let's leave Earth and tour the solar system, because auroras are far from unique to our world. Jupiter has the most powerful auroras in the solar system, and they're visible not just in visible light, but primarily in ultraviolet and X-rays. Jupiter's auroras are driven partly by the solar wind, like Earth's, but they have an additional source of energy. Jupiter's moon Io is the most volcanically active body in the solar system, spewing out tons of sulfur and oxygen into space every second. This material forms a torus, a donut-shaped cloud, around Jupiter's orbit. As Jupiter's powerful magnetic field, which is about 20,000 times stronger than Earth's, sweeps through this torus, it picks up ions and accelerates them to tremendous speeds. These ions rain down on Jupiter's atmosphere near its poles, creating auroras that are larger than Earth's entire diameter and thousands of times more powerful than anything seen on our world. The Hubble Space Telescope has captured stunning images of Jupiter's auroras, showing bright ovals at both poles with dynamic features that change over hours. The Juno spacecraft, currently orbiting Jupiter, has observed these auroras from close range, revealing that some of the processes that create them differ significantly from Earth's auroral mechanisms. It's a reminder that while the basic physics of charged particles exciting atmospheric gases is universal, the details can vary dramatically depending on the specific conditions at each world. Saturn also has auroras, observed both by Hubble and by the Cassini spacecraft during its 13-year tour of the Saturn system. Saturn's auroras are driven primarily by the solar wind, like Earth's, but they also have contributions from interactions with Saturn's moon Enceladus, which emits water vapor that becomes ionized and interacts with Saturn's magnetic field. Saturn's auroras show some unusual features, including spiral structures and patches of emission that don't match simple models, suggesting there are still processes we don't fully understand. Even more surprising, Uranus and Neptune, the ice giants of the outer solar system, have auroras. These planets have magnetic fields that are tilted dramatically relative to their rotation axes and offset from their centers, creating highly asymmetric magnetospheres. The auroras on these worlds don't form neat oval shapes centered on the magnetic poles. Instead, they can appear almost anywhere on the planet as the tilted magnetic field rotates, bringing different regions into alignment with the solar wind. Observations of these auroras are challenging because of the planet's great distance from Earth, but the Hubble telescope and other instruments have captured them, revealing yet more variety in how auroras can manifest. Mars presents an interesting case. As mentioned earlier, Mars lost its global magnetic field billions of years ago. Without a magnetosphere, you might think Mars wouldn't have auroras. But in 2014, the MAVEN, Mars Atmosphere and Volatile Evolution spacecraft, detected evidence of auroral-like ultraviolet emissions in Mars's atmosphere. These Martian auroras are fundamentally different from Earth's. Instead of being confined to polar regions by a global magnetic field, they can appear anywhere on the planet where the solar wind directly impacts the atmosphere. They're also influenced by local crustal magnetic fields, remnants of Mars's ancient global field that are preserved in certain regions of the crust. Even more remarkably, in 2024, a major CME struck Mars, and the solar energetic particles were so intense that they were detected on the Martian surface by the Curiosity rover. The radiation environment became hazardous enough that if astronauts had been on Mars at that moment, they would have needed to take shelter. It was a stark reminder that Mars, without its protective magnetosphere, is vulnerable to space weather in ways Earth is not. Venus, despite having no intrinsic magnetic field, also experiences aurora-like phenomena. The European Space Agency's Venus Express spacecraft detected emissions consistent with auroral processes on Venus's night side. These emissions are driven by the solar wind interacting directly with Venus's ionosphere in a process quite different from the magnetic field-guided mechanisms on Earth. The study of auroras on other planets isn't just about cataloging phenomena. It helps us understand the fundamental physics of plasma interactions, magnetic fields, and atmospheric processes. Each planet is an experiment in how these processes manifest under different conditions. By studying Jovian auroras, we learn about the effects of strong magnetic fields and internal particle sources. By studying Mars, we learn what happens when a planet loses its protective magnetic field. By studying Saturn, Uranus, and Neptune, we learn how different magnetic field geometries affect auroral structure. And all of this feeds back into our understanding of Earth's auroras, helping us build better models, improve predictions, and understand the full range of space weather phenomena that could potentially affect our world. But for most of us, the auroras that matter, the ones we hope to see with our own eyes, are those on Earth. And during solar maximum 2025 to 2026, those auroras are more accessible than they've been in over 2 decades. Not just in the traditional aurora viewing locations like Alaska, northern Canada, Iceland, and Scandinavia, but at mid-latitudes, where millions more people have the chance to witness them without traveling to the ends of the Earth. In places like the northern United States, southern Canada, Scotland, northern Germany, parts of Russia and China, auroras that would normally be rare or absent are occurring with increasing frequency. Every major geomagnetic storm brings auroras hundreds or thousands of miles farther from the poles. Every coronal mass ejection heading toward Earth carries the potential for displays that could be visible from places that haven't seen auroras in decades. And that brings us to the practical question. If you want to see auroras during this solar maximum, if you want to witness firsthand the interplay of sun and earth made visible in light and color, where should you go? When should you look? What should you know? It's time to turn from the science of auroras to the art of chasing them. Technology and the solar maximum, living in a vulnerable world. On February 3, 2022, SpaceX was preparing to deploy 49 Starlink internet satellites, part of an ambitious project to create a constellation providing global broadband coverage. The satellites were launched successfully and reached their initial deployment orbit at an altitude of about 130 miles. The plan was for them to use their onboard propulsion to raise themselves to their operational altitude of 340 miles over the coming days. But something went wrong. A minor geomagnetic storm, classified as G1, barely a ripple compared to the May 2024 Gannon storm, struck Earth shortly after the satellite's deployment. The storm heated Earth's upper atmosphere, causing it to expand and become denser at the satellite's altitude. The increase in atmospheric drag was more than the satellite's propulsion systems could overcome. One by one, 38 of the 49 satellites fell back to Earth, burning up on re-entry. SpaceX lost over $50 million worth of hardware in a matter of days. And it happened during what was supposed to be a quiet period of the solar cycle, still years before solar maximum. If a G1 storm, the weakest category of geomagnetic storm, can destroy satellites worth tens of millions of dollars, what could a G5 storm do during the peak of solar maximum 2025 to 2026? The uncomfortable answer is, we don't entirely know, because we've never had this much critical infrastructure in space during a solar maximum this strong. Let's examine just how dependent our civilization has become on technologies vulnerable to space weather, and what the next 12 to 24 months might reveal about those vulnerabilities. Start with satellites. As of 2025, there are over 9,000 active satellites orbiting Earth, with thousands more planned for deployment in the coming years. These satellites provide services we use every day, often without realizing it. Weather forecasting relies on meteorological satellites. Television and radio often use satellite distribution. Internet service in remote areas depends on satellite connections. Financial transactions are time-stamped using signals from GPS satellites. Even your smartphone constantly communicates with satellites to determine your location, synchronize its clock, and route your calls and data. These satellites face multiple space weather hazards. The enhanced radiation during solar storms can cause electronic upsets, temporary malfunctions where a high-energy particle strikes a critical component and flips a bit in computer memory or triggers a false command. Most of the time, these upsets are harmless, automatically corrected by redundant systems. But occasionally they can be more serious, causing satellites to enter safe mode, lose their orientation, or even fail completely. During major geomagnetic storms, satellites also experience increased drag, as we saw with the Starlink incident. The heating and expansion of the upper atmosphere means satellites encounter more resistance, slowing them down and lowering their orbits. For satellites in low Earth orbit, this can be a death sentence if the drag exceeds their ability to compensate. Satellites can also experience charging effects. During geomagnetic storms, electrons in the magnetosphere are accelerated to very high energies. When these electrons strike a satellite, they can build up electric charge on the spacecraft's surfaces. If the charge difference becomes large enough, it can discharge suddenly, like a miniature lightning bolt, potentially damaging sensitive electronics. The May 2024 Gannon storm affected numerous satellites. While most survived, many reported anomalies that required ground controllers to intervene, putting satellites into safe modes, adjusting orbits, or resetting systems. A few satellites experienced permanent damage to solar panels or instruments. If a similar or stronger storm occurs during the next 12 to 18 months, and given current solar activity levels, it's likely that it will. The impact could be even more widespread simply because there are more satellites in orbit now than there were in May 2024. But it's not just individual satellites at risk. The entire GPS constellation, which consists of about 31 satellites orbiting at an altitude of roughly 12,000 miles, right in the heart of the outer Van Allen belt, is particularly vulnerable. The May 2024 storm demonstrated that GPS can become unreliable or fail entirely during major geomagnetic storms, not because the satellites themselves are damaged, but because the ionospheric disturbances disrupt signal propagation. The implications extend far beyond farmers planting crops. Airlines depend on GPS for navigation, especially for automated landing systems in low visibility. If GPS becomes unreliable during a geomagnetic storm, pilots may need to resort to older navigation techniques, potentially delaying or diverting flights. During the May 2024 storm, some airlines did exactly this, rerouting polar flights to lower latitudes where GPS was more reliable and radiation exposure was lower. Ships at sea use GPS not just for navigation, but for synchronization of shipping schedules and collision avoidance. Financial markets use GPS timestamps to order transactions, critical when high-frequency trading can complete thousands of trades per second. Power grids use GPS timing to coordinate operations across vast networks. Cell phone networks use GPS signals for tower synchronization. A prolonged GPS outage during a major geomagnetic storm, especially if it coincides with other space weather effects like power grid disturbances or satellite failures, could cascade through systems in ways we've never fully tested. Speaking of power grids, the May 2024 storm reminded us that the vulnerability exposed in Quebec in 1989 hasn't been entirely eliminated. While modern grid infrastructure is more resilient, with better monitoring, automated protective systems, and coordinated responses, it's still vulnerable to geomagnetically induced currents. The challenge is that power grids have evolved to become more interconnected and more dependent on complex control systems, which introduces new vulnerabilities even as old ones are addressed. A major geomagnetic storm doesn't just threaten individual transformers, it can affect the entire grid simultaneously, potentially overwhelming operators' ability to respond effectively. After the Quebec blackout, utilities invested in better space weather forecasting, improved transformer designs, and operational procedures for responding to geomagnetic storms. When the May 2024 Gannon storm hit, those preparations paid off. Power companies were warned days in advance. They had time to reduce load on vulnerable transformers, position repair crews, and prepare for potential disruptions. When GICs began flowing through their systems, they were ready, able to take protective actions that prevented cascading failures. But that was a G5 storm, extreme but not unprecedented. If a Carrington-class event were to strike, something several times stronger than the Gannon storm, it's unclear whether our preparations would be sufficient. A 2017 study estimated that a Carrington-level storm could cause power outages affecting 20 to 40 million people in the United States alone, with some outages potentially lasting months in regions where large transformers are damaged and replacements are not readily available. Large power transformers, the kind that step voltage up and down in transmission networks, are not mass-produced. Each one is custom-built for its specific installation, a process that can take 12 to 18 months. If a geomagnetic storm damaged multiple large transformers across a grid, the affected regions could face extended blackouts while replacements are manufactured and installed. Extended power outages don't just inconvenience people, they shut down water treatment plants, disable communication systems, disrupt fuel distribution, interrupt food supply chains, and compromise medical services. A regional blackout lasting weeks or months would be not just an economic disaster, but a humanitarian one. And here's the uncomfortable truth. We don't know if a Carrington-class event will occur during this solar maximum. The probability is low, maybe a few percent at most. But it's not zero, and given the potential consequences, even a small probability demands attention. The May 2024 Gannon storm was a test, and we mostly passed. Power grids stayed up. Satellites largely survived. GPS failed for a few days but recovered. Lives were not lost. But it was just a test. A preview of what could happen if conditions aligned slightly differently, if the magnetic field orientation in the CME were more optimal for driving geomagnetic activity, if multiple CMEs merged to create an even more powerful impact, if the storm struck with less warning. Looking ahead to the remainder of 2025 and into 2026, solar activity is expected to remain elevated. More X-class flares are likely. More coronal mass ejections will erupt. More geomagnetic storms will strike Earth. Some will be minor, creating only modest auroral displays and negligible technical impacts. Others will be stronger, potentially approaching or exceeding the intensity of the May 2024 storm. And there's always the possibility, however small, of that once per century or once per several centuries event, a storm so powerful that it overwhelms our defenses and reveals vulnerabilities we didn't know existed. Space weather forecasting is improving. New satellites are being deployed. Models are becoming more sophisticated. Our understanding of solar physics and magnetospheric processes continues to deepen. But prediction is hard, especially prediction of rare, extreme events. What we can do is prepare. Power companies can continue hardening their infrastructure, improving their ability to respond to geomagnetic storms, and maintaining reserves of critical replacement components. Satellite operators can design spacecraft with better radiation shielding and autonomous systems that can respond to space weather without waiting for commands from ground controllers. GPS receivers can incorporate error correction algorithms that maintain some functionality even during ionospheric disturbances. Emergency response agencies can include space weather in their disaster preparedness planning. And individuals, ordinary people who depend on these systems every day, can gain at least some awareness that space weather is real, that it poses genuine risks, and that the next major event might not be decades away but could happen tomorrow. Because here's the final twist, the reveal that makes this moment in time so significant. The May 2024 Gannon storm occurred before the official announcement of solar maximum. The October 2024 X9.0 flare happened right at the beginning of the solar maximum period. If this is what the Sun can do during the approach to and beginning of its peak activity, what might it do in the months ahead as we move through the maximum period? The window of elevated risk is open now, and it will remain open for at least the next year, possibly longer. But that same window is also an opportunity to witness, to learn, to prepare. An opportunity to see auroras more frequently and more spectacularly than most of us will ever see again in our lifetimes. An opportunity to appreciate the dynamic, violent, beautiful relationship between Earth and Sun that has been shaping our planet for billions of years and will continue long after human civilization has risen and fallen. The Sun is awake. Our technology is vulnerable, and we, for better or worse, are living through it, chasing the lights, where and when to see them. You've learned the science, you understand the risks. Now comes the practical question. If you want to see auroras during this solar maximum, what should you do? Let's start with location, because geography matters enormously. Auroras occur in oval-shaped zones centered on Earth's magnetic poles. During quiet geomagnetic conditions, these auroral ovals remain at high latitudes. But during geomagnetic storms, they expand dramatically, bringing auroras to mid-latitudes and, during extreme events, even to low latitudes. Your latitude determines your baseline chances of seeing auroras and how strong a geomagnetic storm you'll need. If you're at a latitude above about 65 degrees north or south, you're in the auroral zone. Places like Fairbanks, Alaska, Tromsø, Norway, Rovaniemi, Finland, Yellowknife, Canada, Reykjavik, Iceland. These locations see auroras on most clear nights during the winter, regardless of solar activity levels. During solar maximum, auroras there are even more frequent and more intense, with multicolored displays that can last for hours. Between about 55 and 65 degrees latitude, places like Anchorage, Alaska, southern Iceland, Oslo, Norway, Stockholm, Sweden, southern Greenland, northern Scotland. Auroras are common during geomagnetic storms, but rare during quiet periods. During solar maximum, these locations can expect auroras several times per month during active periods. From about 45 to 55 degrees, including northern United States like Montana, North Dakota, Minnesota, Wisconsin, Michigan, southern Canada, northern Britain, central Scandinavia, northern Russia. Auroras are visible primarily during moderate to strong geomagnetic storms. During solar maximum, these regions might see auroras once or twice per month during active periods. Below 45 degrees, auroras are rare, requiring major geomagnetic storms to become visible. But during exceptionally strong events like the May 2024 Gannon storm, auroras can reach these latitudes and even lower. The northern tier of U.S. states like Washington, Oregon, Idaho, Wyoming, South Dakota, Iowa, Illinois, Pennsylvania, New York, Connecticut, as well as southern Britain, northern France, northern Germany, northern China, and parts of Japan, can all potentially see auroras during G4 or G5 geomagnetic storms. And during truly exceptional storms, auroras have been observed from locations as far south as 18 degrees latitude, including Puerto Rico, Hawaii, Mexico, southern Spain, Egypt, and Thailand. So where should you go if you're actively chasing auroras during solar maximum 2025-2026? The answer depends on your budget, time, and tolerance for cold weather. Let me walk you through some options. Fairbanks, Alaska, is often called the aurora capital of North America, and for good reason. Located at 65 degrees north latitude, directly beneath the auroral oval, Fairbanks offers exceptional aurora viewing. The city has relatively clear skies due to its interior location, away from coastal weather systems. Winter nights are long, with less than 4 hours of daylight in December, giving extended viewing opportunities. The infrastructure for aurora viewing in Fairbanks is well developed. Numerous tour operators offer aurora viewing excursions, taking visitors to locations outside the city where light pollution is minimal. Some lodges specialize in aurora tourism, offering heated cabins with large windows and wake-up calls when auroras appear. The downside? It's cold. Really cold. January temperatures average around 10 degrees, with lows sometimes dropping below 40 degrees. You need serious winter gear. And standing outside watching auroras for hours in those temperatures is not for everyone. But if you can handle the cold, Fairbanks during solar maximum offers some of the best aurora viewing on Earth. Yellowknife, Canada. Located in the Northwest Territories at 62 degrees north, rivals Fairbanks for aurora accessibility. Yellowknife sits under the auroral oval and benefits from being away from major light pollution sources. It also has remarkably clear skies. The region is under a continental high-pressure system for much of the winter, resulting in clear, calm conditions ideal for aurora viewing. Yellowknife has developed a significant aurora tourism industry, with numerous viewing lodges located on lakes outside the city. Some offer traditional teepees equipped with heating and comfortable seating, allowing visitors to watch auroras in relative comfort. The city even claims an aurora viewing success rate of over 90% for visitors who stay 3 nights, though this depends on both auroral activity and weather conditions. Tromsø, Norway, at 69 degrees north, offers aurora viewing with somewhat more temperate conditions than Alaska or northern Canada, thanks to the moderating influence of the North Atlantic current. Temperatures in January average around 25 degrees F, significantly warmer than Fairbanks or Yellowknife. Tromsø is also accessible, with direct flights from major European cities and well-developed tourism infrastructure. Aurora tours, often combined with other winter activities like dog sledding and whale watching, are readily available. The city sits in a spectacular coastal setting surrounded by mountains and fjords, making it scenic even during the day. The main downside of Tromsø is weather. Being coastal, it experiences more cloudy days than interior locations. Visitors may need to stay longer or be more flexible to catch clear skies during active auroral periods. Abisko, Sweden, located at 68 degrees north, has developed a reputation as one of the best aurora viewing locations in the world. Abisko sits in a rain shadow created by surrounding mountains, resulting in unusually clear skies even when the rest of northern Scandinavia is cloudy. The Abisko National Park is remote, dark, and spectacularly beautiful. The Aurora Sky Station, located on a mountain accessible by chairlift, offers heated viewing facilities and aurora tours. The combination of clear skies, low light pollution, and excellent infrastructure makes Abisko a top choice for serious aurora chasers. Reykjavik, Iceland, while not directly under the auroral oval at 64 degrees north, offers accessible aurora viewing combined with other attractions. Iceland is easy to reach from both North America and Europe. The entire island is relatively dark outside of Reykjavik itself, and numerous tour operators offer aurora tours to remote locations with clear skies. The advantage of Iceland is flexibility. If auroras aren't visible, there are numerous other activities including visiting geothermal features, ice caves, waterfalls, and the famous Blue Lagoon. For visitors who want aurora viewing as part of a broader trip, Iceland is hard to beat. Finnish Lapland, particularly regions like Rovaniemi, Inari, and Ivalo, offers aurora viewing in what might be the most aurora tourism-friendly region in the world. Finnish Lapland has developed an extensive tourism infrastructure, including heated glass igloos specifically designed for aurora viewing, allowing visitors to watch the sky while lying in bed in a warm room. The region also offers activities like reindeer sledding, ice fishing, and visits to Santa Claus Village in Rovaniemi, For families or those seeking a mix of activities along with aurora viewing, Finnish Lapland is an excellent choice. Now, all of these locations require significant travel for most people and can be expensive. So what if you live at mid-latitudes, say in the northern United States, southern Canada, Britain, or northern Europe? Can you see auroras without traveling to the Arctic? During this solar maximum, yes. Absolutely. The key is timing and preparation. You need to watch space weather forecasts and be ready to act when a major geomagnetic storm is predicted. Several websites and apps provide space weather forecasts and alerts. NOAA Space Weather Prediction Center, tip.noaa.gov, is the official US source for space weather forecasts. They issue watches and warnings for geomagnetic storms, typically 1-3 days in advance when a CME is detected heading toward Earth. Spaceweather.com provides space weather news and forecasts in a more accessible format, with explanation of what current activity means for aurora viewing. Aurora forecast apps, like My Aurora Forecast or Aurora Alerts, send push notifications when geomagnetic activity increases and auroras become likely at your location. University of Alaska Fairbanks Aurora Forecast provides real-time predictions of where the auroral oval currently is and how intense activity is expected to be. When a G3 or stronger geomagnetic storm is forecast and you're at mid-latitudes, here's what you should do. Find the darkest location you can reach quickly. Light pollution is the enemy of aurora viewing. Even during a major geomagnetic storm, auroras at mid-latitudes may be relatively faint, only becoming clearly visible when you're away from city lights. Use light pollution maps to find dark locations within driving distance. Face north. At mid-latitudes, auroras appear as a glow on the northern horizon, with occasional brighter rays or arcs reaching higher in the sky during peak activity. You need an unobstructed view to the north. Give your eyes time to dark adapt. It takes about 20-30 minutes for your eyes to fully adjust to darkness. Avoid looking at phone screens or other bright lights during this time. If you need to use your phone to check forecasts or take photos, use a red light screen filter to preserve your night vision. Be patient. Aurora viewing requires patience, especially at mid-latitudes. Activity can vary over the course of a night. What starts as a faint glow might intensify into bright displays, then fade, then intensify again. Stay out for at least an hour, preferably longer. Dress warmly. Aurora viewing means standing outside, often in winter conditions, for extended periods. Dress in layers, bring hand and foot warmers, and prepare to be comfortable while waiting. If you're interested in photographing auroras, you don't need expensive equipment. A modern smartphone with a night mode can capture auroras, especially brighter displays. For better results, a camera with manual controls, a wide-angle lens, preferably fast, with a large maximum aperture like f2.8 or wider, and a tripod are sufficient. Camera settings for aurora photography typically involve high ISO, 1600 to 6400 depending on aurora brightness, wide aperture, f2.8 or larger if possible. Exposure time of 1 per 15 seconds, shorter for rapidly moving auroras, longer for fainter ones. Manual focus set to infinity. But here's something important. Don't get so focused on photography that you forget to simply watch. Your phone or camera can record the aurora, but your memory of standing beneath those shimmering lights, watching them dance and shift in real time, that's something no photograph can fully capture. Now, when during 2025 to 2026 should you watch for auroras? Solar maximum creates a period of elevated activity, but it's not constant. Some weeks see multiple major storms. Others are quiet. Forecasting which specific nights will have strong auroral displays is impossible more than a few days in advance. But we can make some general predictions. Based on solar activity patterns, geomagnetic storms are most common in the months around the spring and fall equinoxes, March, April, and September, October. This is partly due to geometry. The angle at which the solar wind interacts with Earth's magnetic field is most favorable for driving geomagnetic activity around the equinoxes. We also know that major geomagnetic storms can occur months or even years after the peak of solar maximum, during the declining phase when the Sun's magnetic field is reorganizing after its polarity flip. This means aurora opportunities might actually increase in 2026 compared to early 2025, contrary to what you might expect. For practical planning, here's what I would suggest. If you're at high latitudes or planning to travel to aurora viewing locations like Fairbanks or Tromsø, anytime during winter 2024-2025 or 2025-2026 offers good chances of seeing auroras. The long winter nights from late September through mid-March provide the darkness needed, and solar maximum ensures regular auroral activity. If you're at mid-latitudes hoping to see auroras from home or with minimal travel, you need to be opportunistic. Sign up for space weather alerts. When a major geomagnetic storm is forecast, clear your schedule if possible and head for dark skies. The May 2024 Gannon storm gave about 48 hours notice. The October storms had similar advance warning. That's enough time to make plans if you're flexible. And remember this, during solar maximum, we might get only a few G4 or G5 storms total, or we might get a dozen. We might see auroras visible from Texas and Florida, or the strongest storms might happen to strike when your region is in daylight. There are no guarantees. Aurora chasing requires flexibility, patience, and sometimes luck. But the opportunity is there. Right now, for the next year at minimum, possibly longer. An opportunity that won't come again until the late 2030s, when solar cycle 26 approaches its maximum. The sun has opened a window. The question is whether you'll step through it. The human connection, cultural and historical perspectives. For thousands of years before anyone understood plasma physics or magnetic reconnection, humans have looked up at auroral displays and wondered. And from that wonder came stories, myths, and beliefs as varied as the cultures that held them. To the Sami people of northern Scandinavia, the aurora was the energies of departed souls, or in some traditions, a fox running across the snow so quickly that its tail swept up snow crystals which sparkled in the moonlight. The Finnish name for aurora, revontulet, means foxfires, a reference to this legend. The Inuit peoples of North America had varied beliefs about auroras depending on their specific region and traditions. Some saw them as spirits playing a ball game with a walrus skull. Others believed the lights were spirits carrying torches to guide the souls of the recently deceased. Some Inuit groups considered auroras dangerous, believing they could descend and steal children, and would bring knives outside to keep the aurora at bay. The Cree people called the aurora the dance of the spirits, and believed the lights were the spirits of ancestors dancing in celebration. Other indigenous groups in North America had their own interpretations, some seeing them as warnings, others as blessings, many as signs of communication from the spirit world. In Norse mythology, auroras were associated with the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods. Some traditions held that auroras were the reflections of the shields and armor of the Valkyries, the female figures who chose which warriors would die in battle and be carried to Valhalla. Medieval Europeans sometimes interpreted particularly bright red auroras as omens of war, bloodshed, or plague. Without understanding the physics, they saw the reddened sky as a portent of coming disaster. Historical records of major auroral displays are sometimes accompanied by accounts of the societal disruptions that followed, though whether the auroras actually predicted anything, or whether people simply remembered them when bad things subsequently happened, is impossible to say. In Chinese records, auroras are documented going back over 2,000 years, though they were rarer at China's relatively southern latitudes. When they occurred, they were often interpreted as celestial dragons or signs of imperial significance. These cultural interpretations are not just historical curiosities. They tell us something important about the human relationship with the natural world, about how people have always sought meaning in phenomena they didn't understand, and about the deep psychological impact of witnessing something as unusual and spectacular as a major auroral display. Even today, when we understand the physics of auroras, they retain a sense of magic. The scientific explanation doesn't diminish the wonder. If anything, understanding that you're watching particles that left the sun days earlier, traveled across 93 million miles of space, and are now colliding with Earth's atmosphere to produce light adds layers of meaning that purely mythological interpretations lack. There's also something humbling about auroras. They remind us that we're part of something vast, that Earth isn't isolated, but exists in dynamic relationship with the sun and the larger cosmos, that forces we can't see with our naked eyes are constantly at work, shaping our world in ways both beautiful and potentially dangerous. During the 1859 Carrington event, people who had never seen auroras in their lives stepped outside to find their familiar skies transformed. Telegraph operators, the high-tech workers of their day, watched their equipment throw sparks and catch fire while the sky turned red above them. The experience must have been disorienting, almost apocalyptic for those who didn't understand what was happening. Today, we have the benefit of scientific understanding. We know a geomagnetic storm is particles and magnetic fields, not divine judgment or portents of doom. But that knowledge doesn't completely eliminate the primal response to seeing the sky behave in ways it shouldn't, to watching rivers of green and red light flow across the darkness, to standing beneath a display so bright it casts your shadow on the ground. There's something in that experience that connects us to every human who has ever watched auroras, from Inuit hunters on frozen seas to Sami reindeer herders in Finnish Lapland, to medieval Europeans interpreting what they saw through the lens of their own beliefs and fears. The science has changed, our understanding has deepened, but the fundamental human response, that mixture of wonder, awe, and maybe a touch of primal fear in the face of something so vast and powerful, remains the same. And during this solar maximum, as auroras become visible from latitudes where they're rare or unknown, a new generation is having that experience. People in places like Iowa or Texas or Florida or Puerto Rico, stepping outside during a major geomagnetic storm and seeing something they never expected to see in their home skies, are making their own connections to a phenomenon that has inspired human wonder for thousands of years. We're living through a moment when the veil between everyday experience and cosmic forces becomes thin enough to see through, when the invisible is made visible, when the story being told in scientific papers and space weather bulletins becomes something you can witness with your own eyes. That's the real gift of solar maximum, not just the opportunity to see auroras, though that's wonderful, but the opportunity to feel connected, personally and directly, to the Sun-Earth relationship that makes our world habitable and our existence possible. To stand beneath those lights and know that you're seeing proof, visible proof, that we live on a planet protected by an invisible magnetic field, powered by a star that could destroy us but instead sustains us, part of a cosmos that is strange and beautiful and sometimes dangerous and always worth paying attention to. Looking forward. After the maximum solar maximum won't last forever. Eventually, perhaps by mid to late 2026, sunspot numbers will begin to decline. The sun's magnetic field, having flipped during the maximum, will start to organize itself again. Geomagnetic storms will become less frequent. Auroral displays will retreat toward the poles, and solar cycle 25 will transition into its declining phase, moving toward the minimum that will mark the beginning of solar cycle 26. But the story doesn't end there, because every solar cycle is different, and solar cycle 25 has already surprised us in significant ways. Remember, this cycle was predicted to be weak, comparable to the previous cycle, which was the weakest in a century. Instead, it's been significantly more active, with more sunspots, more powerful flares, and stronger geomagnetic storms than forecasters anticipated. Why? We're still not entirely sure. Some solar physicists have suggested that solar cycle 25's vigor might be connected to longer-term variations in the sun's magnetic field, cycles within cycles that modulate the strength of individual 11-year cycles. Others think we might simply not understand the solar dynamo, the mechanism that generates the sun's magnetic field, as well as we thought we did. What this means for the future is uncertain. Will solar cycle 26, expected to begin around 2030, also exceed predictions? Or will it return to the weaker patterns we've seen in recent decades? We don't know. And that uncertainty is both frustrating for scientists trying to predict space weather impacts, and exciting for those of us who appreciate that the universe still has the power to surprise us. One thing we can say with confidence is that the knowledge gained during solar cycle 25, and particularly during events like the May 2024 Gannon storm, will improve our understanding and our preparedness for future cycles. Every major geomagnetic storm is a learning opportunity. Researchers analyze the data, comparing predictions to observations, identifying where models succeeded and where they failed. Engineers examine how spacecraft and ground systems responded, identifying vulnerabilities and developing improved designs. Emergency planners review response procedures, looking for ways to improve coordination and communication. The May 2024 Gannon storm, despite its intensity, did not cause catastrophic damage. Power grids remained operational. Satellites survived. The primary impact was to GPS systems, and even that was temporary. In a sense, we got lucky. But we also learned. We learned which systems are more vulnerable than we thought. We learned what kinds of advance warning are most useful for operators trying to protect infrastructure. We learned that our forecasting has improved, but still has room for further refinement. And perhaps most importantly, we learned that space weather is not a theoretical concern, but a real, immediate challenge for our increasingly technological civilization. Looking beyond solar cycle 25, some researchers are developing more ambitious space weather forecasting capabilities. Ideas include placing spacecraft at multiple points in space to provide different views of the sun and incoming CMEs, improving our ability to predict their impacts. Others are working on machine learning algorithms that can identify patterns in solar activity and predict flares or CMEs before they occur. Some scientists have even proposed solar missions that would place spacecraft much closer to the sun than ever before, perhaps within the orbit of Mercury, where they could observe the earliest stages of CME formation and provide additional warning time for Earth. But technology is only part of the answer. We also need societal preparedness. Awareness that space weather is real, understanding that major events, while rare, can have significant impacts. Plans for how to respond when those impacts occur. The challenges are significant, but so is the opportunity. We're living at a unique moment in human history, a time when we depend on technology vulnerable to space weather but also have the scientific knowledge and technical capability to understand, forecast, and potentially mitigate those vulnerabilities. What happens next depends in part on decisions we make now. How much do we invest in space weather monitoring and forecasting? How much do we prioritize hardening critical infrastructure against geomagnetic storms? How do we balance the costs of preparation against the uncertain probability of extreme events? These aren't easy questions, and they don't have simple answers. But they're questions worth asking, especially during a solar maximum that has already demonstrated the sun's capacity for surprise. For now, though, as we move through 2025 and into 2026, the immediate future is clear. The sun will remain active. Geomagnetic storms will continue to occur. Auroras will dance across high-latitude skies and occasionally venture much farther south. Our technology will be tested, sometimes stressed, hopefully resilient enough to withstand what the sun throws at us. And we, standing beneath skies illuminated by the interaction of solar particles and terrestrial magnetism, will have the opportunity to witness, to learn, and to remember that we live on a small planet, orbiting a vast star in a dynamic, sometimes violent, always beautiful cosmos. The story of Solar Cycle 25 isn't over. We don't yet know when the true peak occurred or will occur. We don't know if the strongest storm of the cycle has already struck or is still to come. We don't know if we'll see another Carrington-class event in our lifetimes, or if the sun will spare us that particular test. But we do know this. Right now, at this moment, we're living through something remarkable. A solar maximum stronger than predicted, creating auroras more accessible and more frequent than they've been in over 2 decades, testing our technology in ways we've prepared for but never experienced at this scale, revealing both our vulnerabilities and our resilience. It's a gift, really. A chance to see the invisible made visible. A window into the dynamic relationship between Earth and Sun. An opportunity that won't come again until the next solar maximum arrives, probably in the mid to late 2030s. So if you have the chance, if the forecasts predict a storm, if the sky is clear and you're somewhere dark enough to see, step outside. Look north. Be patient. Wait. And if you're lucky, if everything aligns, you'll see those lights. Those ancient, eternal, ephemeral lights, dancing across the darkness, connecting you, through physics and light and the motion of charged particles, to the star that gives us life, and to the magnetic field that protects us. You'll see the northern lights during solar maximum, and you'll remember it for the rest of your life. Closing. A night under the lights. The sun is settling now, moving toward its next quiet period. But not yet. Not for months, possibly a year or more. The window remains open. Tonight, somewhere above the Arctic Circle, auroras are dancing across the sky. Green curtains billow in a silent wind. Red glows pulse along the northern horizon. Rays of light shoot upward, following magnetic field lines invisible to the eye, but written in the movement of those ghostly beams. Someone is watching. Perhaps a local who has seen auroras 1,000 times, but still steps outside when the sky comes alive. Perhaps a visitor who traveled halfway around the world for this moment. Perhaps someone who simply glanced up and saw something they'd only imagined, now real, now impossibly vivid against the darkness. They don't need to know about plasma physics or magnetic reconnection or the solar dynamo. Those things enrich the experience if you understand them, but they're not required for wonder. The lights speak a language older than words, a language of beauty and motion and color that bypasses the analytical mind and strikes something deeper, something primal, a response that connects us to every human who has ever watched the sky transform and felt that mixture of awe and insignificance that comes from witnessing forces so much larger than ourselves. You've journeyed with me tonight through the science of auroras, from the churning interior of the sun to the upper reaches of Earth's atmosphere, from the discovery of the solar cycle to the surprising strength of solar cycle 25, from the physics of atomic emissions to the vulnerabilities of our technological civilization, from ancient myths to modern forecasts. But in the end, it comes back to something simple. The lights, the sky, the invitation to step outside and look up. During this astronomy maximum, that invitation is extended more widely than it has been in over 20 years. More people at more latitudes have the chance to accept it. Will you? When the forecasts call for a storm, when the sky is clear and the night is dark, will you find a place away from city lights and give yourself the gift of patience, of waiting, of watching? Because the lights are calling, the sun is awake, and Earth's magnetic shield is glowing with the evidence of invisible battles fought on scales we can barely comprehend. This moment won't last forever. Solar cycles come and go. The peak will pass. Activity will decline, and the chance will fade, not forever, but for another decade. But right now, tonight, the window is open, the northern lights are dancing, and you have the chance to witness something that people have traveled to the ends of the earth to see, something that has inspired myths and legends and scientific discoveries, something beautiful and dangerous and ephemeral and eternal all at once. Sleep well tonight, knowing that above you, even if you can't see them, even if you're too far south or the sky is cloudy or the sun is momentarily quiet, those processes are still happening. The solar wind is still blowing. Earth's magnetic field is still deflecting it. And somewhere, auroras are still dancing. May you find your way to them during this solar maximum, and may the memory of those lights, if you're fortunate enough to see them, stay with you through all the quiet years that follow. Thank you for drifting through this cosmic journey with me. If this exploration brought you peace, wonder, or simply a quiet way to end your day, consider subscribing to the channel. It helps others find their way here, one curious mind at a time. Until the next journey, rest well, dream softly, and remember to look up. The universe has stories to tell, and the sky is full of them. Good night.